Hello everybody. Today I'm going to do a video on how we actually go about finding angle measures. Now, this is specifically going to be using trigonometry. So this is going to be finding missing angle measures in right triangles, given that you don't have two of the angles. Typically whenever you've got a right triangle and they have you excuse me, I'm so sorry. Typically, whenever you've got a right triangle and they have you actually looking for a missing angle, they'll usually give you one of the two. Like, they'll say, hey, if this is 45 degrees, what's the measure of angle theta? And you'll sit there and you'll do, okay, well, 180 degrees is what makes up a triangle, and you'll subtract 45 from that, and you'll subtract 90 from that. And that'll get you 45 degrees, and bada bing, bada boom, you're done. Nothing else is needed. Now, that's all well and good, but what if you don't have these two angles? What do you do then? You can't actually go about determining the measure of an angle without that. Now, there are a few tricks of the trade that come with determining the measure of angles, depending on the lengths of certain sides when compared to one another. And that's usually dealing with what we call special right triangles, which is another topic which we'll take a look at someday. But right now, we're going to focus on what are called what would be more known as non-special right triangles. So, we're going to assume that, hey, I want to know what this bottom angle is. But all they've given me is that, alright, well, this has a measure of 6, and this has a measure of 10. And that's it. And that's all I've got. And they want to know what this is. So how do you go about figuring this out? Well, this is where trigonometry comes into play. So, first off, I've got to label my opposite, my hypotenuse, and my adjacent side. Well, this is my hypotenuse, 10. It's the longest side and the side across from the 90-degree angle. Now, if you recall, the side that the angle in question will always touch two sides. One's the hypotenuse. The other one is what's known as the adjacent side. Therefore, the side that doesn't touch is known as opposite. All right. So, next, you've got to look at this and figure out, okay, given the sides that actually have numbers and what they are in relation to theta, which trig function suits this? So, remember, there are three trig functions, or at least there are three main trig functions we use. There are 6 total. So we're going to be looking at SOHCAHTOA here. Some old hippie caught another hippie tripping on acid, if you recall. So remember, some old hippie, that means sine is equal to the opposite over the hypotenuse. Cosine is adjacent over hypotenuse, and then tangent is opposite over adjacent. Squeeze that in there. All right. So, we need to look to see which sides we have, and therefore we'll know which trig function to use. Well, looking at this, the adjacent and the hypotenuse, the only ones that have something, so that means we need cosine. So I'm going to write cosine theta equals, now my adjacent side was 6, and my hypotenuse was 10. So I'd be writing those down. Now, typically this is the part where it's like, alright, you would simplify the fraction. We can do that, but for this, it's not exactly necessary, so you don't have to do this part here. Now, the measure of the angle is represented by the symbol of theta. Now, right now, I've got the cosine of theta equals 3/5. Alright, so how do I get rid of the theta? Well, this is where we have to do something interesting. So, for every function, there's what we call the inverse function. Essentially, the inverse function is a completely separate function from the original, but in such a way that the two of them cancel each other out completely. So, what we're going to need to do here is, I need to get rid of the cosine part on the left. To get rid of that, I've got to use its opposite. Think of this kind of like if you had something adding to cosine and you wanted to move it to the other side. Then you would subtract it. Or if there was or if it was 3x equal to 2, and you wanted to get 3 away from x, you divide 3 on both sides. In essence, this is the same idea. So what I'm going to do is I'm going to take the inverse cosine of both sides. Now, I didn't quite leave myself enough room here on the right, but you'll see what I mean. Now, like I said before, by taking the inverse of a function, you cancel out the original. Therefore, inverse cosine and cosine disappear. And what remains is theta. So that means theta is equal to the inverse cosine of the fraction 3/5, or 6 divided by 10 if you didn't rewrite it. Alright, so what good does that do me? Well, as is, not a lick. But this is where the calculator comes in. Now, and what you're going to be doing here is going to be very calculator heavy. Unless you happen to be doing things old school and using a trig table. If you don't know what that is, I'll let you look that up. It's not exactly fun. Okay, so let's go to the calculator. Now, here I'm going to use my phone again. So, if you open your phone up and you have your phone sideways, this is typically what shows up. And remember, this is Android, not iPhone. So, for me, the way I have to do this is I have to hit this button here. That brings up a whole different table of stuff on this next screen. Now, since I'm using inverse cosine, I want to make sure I hit cos -1. And this makes this a cos here. So this basically stands for arc cosine, which is in essence just inverse cosine. And I'm going to do, not 35, 3 divided by 5. And that gives me what is approximately 53.1 degrees. And that would be the measure of that angle. Now, if you're using a actual calculator, let's switch my phone around. So this is that Calculate 84 app I mentioned in a video ago. To bring up the inverse trig function, if you look here, you'll see right above tan, cos, and sin. You see sin -1, cos -1, tan -1. So if I hit second cos and do 3 divided by 5, I get 53.13, etc., etc., etc. So about 53.1. And there you go. Now, this works the exact same way no matter which trig function you have to use, whether it's sine, cosine, tangent, any of them always work the exact same way. So, I'll do a couple more. Finding the inverse of the angles, once you get it set up, it's not difficult. It's just a simple matter of typing things in the calculator. But setting them up can be a little difficult. It's definitely a little tricky. Getting the hang of recognizing which two sides you have and then accurately going to whether you use sine or cosine. So, let's do another one. So let's say we've got this here. Here's my theta. And let's say my numbers are 15 and 20. Now, same idea. Identify your adjacent, your opposite, and your hypotenuse. In this case, here's my hypotenuse. This side would be my adjacent. This side's my opposite. All right. From there, I determine, is this sine, cosine, or tangent? Well, the only two sides that have numbers on them are the opposite and the adjacent. So sine is opposite over hypotenuse? Nope. Cosine, adjacent over hypotenuse? Nope. Tangent, opposite over adjacent? Correct. So tangent of theta, make sure you write the fraction correctly. If you put the numbers in the wrong spot, then this can get very bad very quickly. And just do something off camera real quick. Yeah, there we go. So, tangent of theta of 20 over 15. To get rid of tangent, oh, don't forget, you can simplify this, but it is not necessary. Do it if you want, but I'm not encouraging you to do so. To get rid of tangent, I want to take the inverse tan of both sides. Cancels out tans here, leaving theta. Then theta equals the inverse tan of 4 divided by 3. Then bring in our calculator. Second tan of 4 divided by 3. And it equivalates out to 53.1 again. There you go. So, we'll do one more, and then something else I want to talk about real quick. So, let's say we've got this one. We'll throw theta up there. Do 5 there. 13 up top. There we go. So in this one, hypotenuse, adjacent, opposite, opposite and hypotenuse, the two that have numbers. So we want to use sine in this case. So sine of theta equals 5 over 13. So inverse sine of both sides. Cancels out. Theta equals inverse sine of 5 divided by 13. And that's where the calculator comes in. Second sine, 5 divided by 13, gives us 22.62. Or basically 22.6 degrees. So, there we go. Again, it doesn't matter which trig function it comes down to. All three trig functions work the exact same. So whenever you set it, so the hardest part, like I said, is setting it up. Once you identify which side's opposite, adjacent, hypotenuse, you use your trig function correctly, and There you go. Now, make sure, though, that your calculator is set in degree mode, because if it's not set in degree mode, you can get something very different. So, as you can see here on my calculator, it is set to degree. I'm going to change it to radian real quick. And I'm going to type the exact same thing in. 13. As you can see, I get a completely different number here. I get 0.39. So, make sure your calculator is set to the correct mode. More importantly, if you ever pick up a calculator that you haven't been dealing with directly, or you're not sure if someone's picked it up before you go doing any sort of math on it, guys, especially anything dealing with angles, always check the mode on your calculator. It takes absolutely no effort to change it from one to the other, and it can save you a lot of headaches from doing a whole assignment incorrectly and having to go back and do it. So, now, there's one additional thing I want to talk to you about, and it's essentially word problems real quick. I mentioned these in the last video, but I didn't really go into detail about them. I wanted to take a moment to go over them real quick with you. So, typically, whenever we're dealing with trig word problems, there are one of two things that we're looking at. There are what are known as angles of elevation and angles of depression. Now, when you talk about angles of elevation, essentially, what the word problem is talking about is if we've got a person standing here and they're looking at something, and something is known as an angle of elevation if the object that they're looking at is up here, because that means that that means the person is literally having to take their eyes and shift them upward in order to see the object that is being spoken about here. And an angle of elevation typically appears right here. So, a common scenario for an angle of elevation is, let's say Carl is about 5 feet tall, and he's looking at looking at the top of a tree that is unknown, and the angle of elevation is 20 degrees, and they want to know, what's the height of the tree, let's say. Well, and they'll give you some sort of information like, say Carl is standing 25 feet away from the tree, and they want to know, hey, what's X? The height of the tree. So, in a case like this, and keep in mind, I'm making this up off the top of my head. The scenario, that is, not the concept. To do this, we have a right triangle, because we assume that the tree makes a right angle with the ground. You kind of have to assume that. And we know our angle down here is 20 degrees. So this 20 degrees would be our reference angle, which means that 25 would be the adjacent. This would be the hypotenuse, and our x here would actually be the opposite. So we would set this up like we would a normal trig problem. Since we're using the opposite and the adjacent, that means we'd be using tangent. Since we actually have a number for the reference angle, we'll put 20. Tangent is opposite over adjacent, so you do x over 25, and we'd solve. Remember, when you have the number on the bottom, simply shift it over in front of your trig function. Instead of taking a bunch of extra movement to shift stuff, then we can simply pick up the calculator and make sure we type numbers in correctly. That unfortunately happens really often. And according to this says that the tree is about 9.1 feet tall. So not very tall tree. But this is actually a trick problem because X here is only representing this portion of the tree. And the thing is, the tree actually continues all the way down to the ground. Because remember, his eyeballs are not on the ground. They're in the air. So this additional 5 feet here actually comes into play. So that actually means that the tree itself is 14.1 feet tall. So this is a pretty common problem in trigonometry. It's an easy problem that can be very the trick can be very easy to miss. So you always want to keep in mind of like, okay, where is the angle in relation to the ground? Is the angle actually on the ground, or is the angle actually hanging somewhere in the air? Always pay attention to the problem and where items are. So this is essentially an angle of elevation. Now, the other type of angle that you commonly come across in word problems is what's known as an angle of depression. So, angles of depression are formed a little differently from angles of elevation. Angles of depression are formed not by looking up, but by looking down, as you might guess. Now, a lot of angles of depression are formed by either someone up on the top of the building, or a lot of problems deal with like a plane flying over. But here's the kicker. A lot of angles of depression can be redrawn as a right side up triangle. But you've got to be careful of where you put your angle, because in fact, if I was to redraw this triangle a little bit, the angle of depression, if you were to draw it as a right side up triangle, would not be up here, but it would be down here. These two angles would be equivalent. Now, why is that, you might ask? Well, this actually pulls a lot of geometry concepts together. So, this line is essentially what is known as a transversal. A transversal is a line that crosses two parallel lines. Now, in this case, I actually have two sets of parallel lines. How do I know that they're parallel? Because I made two right angles. Because these two are right angles, that implies that these two angles would also be right angles. Therefore, these two lines never touch, and these two lines never touch one another. Therefore, this angle will always be equivalent to the angle over here. Likewise for the angles on the opposite sides of the thetas that I drew. So, and that's why the angle is actually down the bottom here, where you would normally expect the angle of elevation. Basically, whenever you draw an elevation or depression problem, your theta should always be in the same position as you would think the other one would be. If you were to redraw the triangle as that. Typically with angles of depression problems, this is the picture that comes to mind. This here, where you have the upside down triangle. This is what comes to my mind the most, because I always think of, all right, my head is tilting down to look at something below my line of sight. Because typically the line of sight for a person is just straight across. So, typical problem here would be we've got, let's say, we've got a little helicopter, and you now get to be subjected to my horrific drawing skills. So we have our terrible looking helicopter here. I'd apologize for this, but no, not happening. And let's say that this helicopter is, I don't know, say 1,500 feet off the ground. And they're traveling, and the distance from where the helicopter is to where their landing pad is say, I don't know, 1,000 feet away. And the pilot wants to know, hey, what is the angle that they have to take their helicopter in at in order to land safely? So in this case, same idea. Hypotenuse is here, opposite goes here, adjacent goes here. This would be a tan problem again. Tangent of theta equals 1,500 over 1,000, which is basically, 3 over 2? Yeah. Inverse tan of both sides. So you could either rewrite this as 3 over 2 or not bother. Either way is not going to make a difference. 1,500 divided by 1,000. Therefore, the angle of descent needed to land safely would be about 56.3 degrees. And there you go. So, there you go. So that's all I've got for how to find the measures of angles, as well as a little extra bit on angles of elevation and depression. All right. So that's it. If you've got questions, send me a message, leave a comment, and well, take care of yourselves, guys. Okay. Bye.